5, 4, 3, 2, 1. Engines full power, and liftoff of CRS-27. Go Falcon, go Dragon.
Thanks to advancements in rocket technology, space has never been more accessible. In the past 7 years, there's been more than an 800% increase in the number of spacecrafts launched into orbit. This second space age is driven by the development of miniature spacecrafts which are less complex and cheaper to make. Satellites rely on Earth's magnetic field to make rotational maneuvers in space by utilizing their ADCS, the Attitude, Determination, and Control System. To test the ADCS on Earth, 3-axis magnetic field chambers called Helmholtz cages are used to simulate the low Earth orbit magnetic field environment. There are a select few companies that design Helmholtz cages. However, these options are over-engineered for testing these miniature spacecrafts. Thus, a hole in the market exists to develop a modular, simple design for the second space age.
To fill this hole in the market, we built Flux Vault, a modular, iteration-friendly, benchtop Helmholtz cage for the validation of attitude, determination, and control systems.
How does a Helmholtz cage work? Well, first you start with 2 copper coils with identical radius r. Then these copper coils are spaced a radius apart and connected in series. Then a voltage is applied to these coils, which creates a static magnetic field which is flat within the center. Taking 3 of these and labeling them X, Y, and Z, you're now controlling 3 separate magnetic field vectors. Assembling all these coils orthogonal to each other will then create a Helmholtz cage, which in the center creates a controllable magnetic field.
To realize the 3-dimensional requirement for our product, custom 3D printed loops were designed to accommodate the integration of 3 Helmholtz pairs with 3 different radii. To ensure an equal magnetic field is generated, the number of turns and sizes were optimized. The Z pair, the X pair, and the Y pair are therefore in increasing sizes.
To maximize resolution and be able to provide even small magnetic fields, we decided to use an analog solution as opposed to the classical pulse width modulation scheme you often see in inductive drivers. So with our STM32 microcontroller, we are able to drive using I2C 3 separate digital to analog controllers on 3 chains, which will then drive an op-amp and to boost the voltage, and then use a BJT to boost the current, which allows us to drive up to 30 volts and 2 amps between our coils, which will give us about 2 Gauss. And then we use an H-bridge to switch the direction only, which gives us plus or minus 2 Gauss range on our coils.
In the center of our device, we have a 3-axis magnetometer. As we turn our device on, you can see the compass start to rotate as we feed it an alternating field. Over SPI communication, we can communicate with the magnetometer to a real-time live application, where you can see the field alternate between plus or minus 2 Gauss.